Okay, here let's look at some example of work and potential energy. In a lecture, we define the potential energy, and it is actually the work due to some conservative force. Where the conservative force is a force that work done by the force only relate to the position. It doesn't matter what the path that it took to reach to the position. We have two kinds of potential energy, or two kinds of conservative force or done work that can be characterized as potential energy. We have gravitational, that we use of G to represent it. We also have a spring, which is the spring potential energy, that we use of S to represent it. Each one of them has a different equation. When you use those equations, I wanted to actually tell you the symbol that we use here, the H, could be represented like the y direction, and normally it's the y direction, like vertical direction. Where the X doesn't have to be in a horizontal direction. The spring can also change vertically. It can change horizontally, but it can also change vertically. The X simply represents the change of the length along the direction of the spring. The work is defined as the force times displacement and multiplies the angle of the cosine, where the angle is between the force and the direction of the motion. Now, let's look at the example. But before we go into the example, let me just write down the work and the potential energy equation, or the work and energy equation. If we don't have a kinetic energy, then the work is simply is equal to the change of potential energy. And we have two kinds of potential energy. So we can say the change of potential energy due to the gravitational, or the change of potential energy due to the spring. If you only have the spring, or you only have the potential energy due to the gravity, then you can eliminate the other one. And when we define the potential change, the change meaning the final minus initial. So this is actually equal to u sub G of a final minus u sub G of an initial, and plus the US of final minus US of initial. Okay, we use a lot of subscript, but I hope that you understand which symbol represents what. And if there's no work other than those conservative force in the system, then the work will be equal to 0 as well. Okay, so those are the basic things that you need to know. Let's look at the first example here. We have a spring gun. It was compressed to a certain distance, and the distance is actually equal to 0.25 meter. It's 25 centimeters. So from here to here is 0.25 meter. When the spring reached to the top, which is y equal to 0, it is the unstretched spring length. So 0.25 is like a pre-compressed distance. We wanted to use the idea of work and potential energy theory to find what is the maximum height and the ball can fly up to, away from the spring gun, which is away from the 0 position. Now we can mark the state before we actually to write down the equation. The equation is there, so let's just mark down what is the state of the initial and what is the state of the final. When the ball is here, this is the initial state. When the ball reaches to the maximum height, this is your final. When you are in the initial, the velocity is equal to 0. When it's at the final state, the velocity also equal to 0 because it's the maximum height. When you reach to the maximum height, there's no speed, right? Otherwise, it will keep on going. So both state has the velocity equal to 0. That's why we don't have to consider about the kinetic energy. The only thing we need to consider is the potential energy. However, in this system, the ball affected by two things. It is affected by the gravity, is also affected by the spring force. The spring force only acts on the object for certain distance, that is the 0.25 meter, just right before you reach to the tip of this gun. So how do we use this? We're not going to consider any of the friction force, any other kind of force, or like air resistance is not going to be considered in this case. Then we can simplify this to be the situation there's no work. So if you look at the equation we just write over here, work of the non-conservative force is 0. And this is going to be equal to the change of potential energy and the change of the spring energy. So we're going to write the change of U sub G plus the change of U sub S. Now, what is the change of U sub G? Then you have to write down what is the initial high and what is the final high. So our initial high is what? That is not equal to 0. If you define here as 0, this will be negative 0.25 meter. Your final high is going to be the high max, which is something we try to find out. So we write U sub G is equal to M times G times the final high minus initial high. And what is the M? That is 1.5 kilogram. And your G is 9.8 or 9.81 meter per second squared. And what is the change of high? The change of high is H max minus negative 0.25. Okay, don't just write negative. Don't just try write minus 0.25. This is the correct answer. And we can also look at the change of the spring potential energy. That is equal to 1/2 k x squared. Okay, and you have the final one minus the initial one. Well, in this case, the x is also y because it's oriented vertically. So what is the initial change of the length? Initially, the change of the length is actually equal to negative 0.25 meter. And what is the final? Where is the final? Well, for the spring, this is the final for the spring. The final, the state of the spring is just at the nozzle of the spring gun. So the final X is going to be 0. That means it's unstretched. It is just neutral. Therefore, when you write this will be 1/2 times K, and the K is 300, and multiply with the XF, which is 0 minus XI is negative 0.25 squared, and that will be the change of the spring force. the spring potential energy. Then you sum these two together, make it equal to 0, then you can solve for this problem. So let's sum all these together. So if you use calculator, let's use the calculator to find out what this is. This is 150 times 0.5 squared divided by 9.81. You can also verify the result with me. I got the H plus 0.25 equal to 0.638 meter. And this is a meter as well. Therefore, the H is equal to 0.388 meter. And that's the answer for this question. Okay, just be careful this part here. The people probably will write it wrong as the H minus, which is H plus, or somebody will forget about this 0.25, then you will be wrong. Okay, here's the second example. We have an object on a ramp and is attached to a spring. And if we just compress the spring, let me just erase some of them. If we compress the spring, and we actually try to find out how much this can be compressed. Okay, so initially it's at the rest. When it's fully compressed, it will be compressed by a certain amount. And we want to find out how much can this box compress the spring. We want to find this. The object is given to you is the 10 Newton, so this one has the weight, which is 10 Newton. It also gives you the angle of this ramp. And there's no friction at all. We don't want to consider about the friction. The spring has a spring constant. The K is 100 Newton per meter. Okay, then we want to find the data X. And the thing we consider at here is the box. And if you look at this, how many force acting on this box? Now we have a weight, we have a spring, and what is the direction of the spring force? It's compression, so the spring force will go in this direction. This is your spring force direction. Are there any other force acting on the object? Well, if you have an interface between the ramp and the object, you should have a normal force as well. So we have three different forces. If you have three different forces, and you have to think about what other force is going to do with the system. Are they going to do work, or are they going to become the potential energy? In this case, we just told you, if you have an object attracted by Earth, then the potential energy due to a gravitational force is your gravitational potential energy. So we have the way it will cause the use of G, which is the potential energy. We also have the spring. The spring force will cause the use of S, which is elastic potential energy due to the spring. What about the normal force? We didn't tell you the normal force is a conservative force, or the normal force only exists when you have some direct contact. But this normal force is not going to do any of the potential energy. It's also not going to do any work. And what is the reason it's not going to do work? The reason is the object is not going to moving along the direction of the normal force. So there's no displacement. If it moves, it will be away from the ramp. It's going to fly up to the ramp. So it's not going to do any of the work. So in this case, we don't really need to consider about the normal force. It's not going to exist in the energy equation. Then let's look at the equation that we had before. We say work is equal to the change of u sub g plus the change of u sub s. Because we don't have any of the work, and we can make this one equal to 0. If we do consider about the friction force, then you will have some work because the friction force will do work. What happens if we do have friction? If you have a friction, then this equation will be a little bit different. If you do have a friction, then the work will have some value, where the value is going to be friction. And because the friction force is opposite to the direction of the movement, this will be the friction force multiplied with the change of x. That will be your work done by the friction force. And on the right hand side, you're going to have the same thing, the change of u sub g plus change of u sub s. And what is the friction? This friction force is mu k times m. Okay, so that's your friction force. Oh, well. Okay, let's look at the case that we don't have the friction. Let's see how we solve this. Well, we only care about change of x and change of the u sub g, change of the u sub s. And these are all related to the change of height or change of the length of the spring. And because this is an angled direction, the change of the height is the change of this. If it changes to this position, let's say for example, then this is the amount of change of x. This is your amount of the change of the y. The change of the y is the change of the potential energy. It is not the same as the change of the x direction. And the change of the x direction and change of the y direction has a relationship. We know this angle is 41 degrees. Based on the 41 degree, we can write an equation. The tangent of 41 degree is actually equal to the change of y over change of x. So we can simply say the change of y is equal to tangent 41 multiplied with the change of x. And let's look at what is the change of potential energy and change of the spring energy. The change of potential energy starting from this position to this position. So this is your starting point. This is your final point. And this is going to be the final point of the spring. This is the final position of the gravitational, and the other part is the gravitational as the final position for the spring. So if we make the final to be at the bottom and initial at the top, if we make this y is equal to 0, the two position, the y will be negative of change of y. If we make this one position 1, that x equal to 0, then this x at here at 2, the x will be negative change of x. This will be this is the amount of the change of the x. So this should, so x is the change, negative change of x. All right, so let's look at the potential first. That is going to be mass times gravitational constant multiplied with the change of the y, which you're going to have the y final minus y initial, and that is 10 Newton, which is the mass times the gravitational constant, multiplied with the final is y sub 2 negative change of y minus 0. What about the spring? Spring is 1/2 k, and the change of x final squared minus change of x initial squared. Change of the initial equal to 0, so I only have 1/2 k change of x squared. Now we have these two equations. We also know that k is equal to 100. We also know x and y are related by this equation here. Then we sum these two together, has to be equal to 0. This will be a negative 10 times change of y plus 1/2 k change of x squared. Let's replace the change of y by this equation here. And what is the k? K is 100. This is change of x squared. Then you solve this equation, you can see we can cancel out one of the change of x. And this is negative, we can put it to the other side, and then you can solve for the change of x, and that's the thing we try to find. So if you put all these numbers in there, and I think you're supposed to get 0.174 meter. And that's the solution for this problem.